Imagine pointing the most powerful telescope ever built at a patch of sky smaller than a grain of sand held at arm's length. Not at a star, not at a nebula, at nothing. Pure, empty, lightless nothing. And then imagine that when the light finally comes in, after days of collecting photons that have been traveling for over 13 billion years, the image shows you something you did not put in your models. Something that your equations said could not be there yet. Something so small it looks like a flaw in the sensor. A smudge, a flicker. Scattered across every single deep field image the telescope sends back. Dozens of them, then hundreds. Tiny, compact, impossibly bright, and unmistakably red. The universe apparently did not read the textbook. These are the little red dots. And what they are doing to astrophysics is not a minor correction. It is a full reckoning. For decades, we had a story about how the universe built itself. It starts with the Big Bang. Everything compressed into a point of unimaginable heat and density and then expanding outward. For the first few 100,000 years, there are no stars, no galaxies, only a hot, thick fog of hydrogen and helium plasma so dense that light cannot travel through it. The universe is opaque, blind to itself. Then around 380,000 years in, the fog clears. Atoms form, light escapes for the first time, and over the next several 100 million years, gravity quietly does its patient work, pulling gas into filaments, filaments into clumps, clumps into the first primitive stars and galaxies. It is a slow process, majestic but slow. The universe needed time to assemble its largest structures. The biggest black holes, the most massive galaxies. Those came later, built up piece by piece over billions of years of collisions and mergers and the steady accumulation of matter. That was the model. That was what every simulation, every equation, every successful prediction of the last 40 years had told us. The James Webb Space Telescope was not built to break that model. It was built to see it in action, to watch the first galaxies flickering to life at the cosmic dawn, to witness the universe building itself from scratch, and to confirm in exquisite detail what we already expected to find. It did not do that. JWST launched on Christmas Day 2021. After a 6-month deployment and calibration process that engineers described as flawless, the telescope opened its golden eye on the deep universe for the first time in the summer of 2022. The first images were extraordinary, dazzling curtains of gas, ancient galaxies bent into arcs by the gravity of closer clusters. A universe that looked on the surface exactly like the simulations had predicted. But then the scientists started looking at the data carefully, and almost immediately something was wrong. Almost every deep field image contained them. These small, compact, intensely red points of light. They were not stars, they were not artifacts. They were real objects at real distances broadcasting real light that had been traveling for almost the entire age of the universe. Researchers dated them quickly. These objects existed between roughly 600 million and 1.5 billion years after the Big Bang. In cosmic terms, that is extremely early. The universe was not even 10% of its current age. But here is what no one expected. They were everywhere. Jorit Matthey, an astrophysicist at the Institute of Science and Technology, Austria, led one of the first major studies on these objects. His team coined the name that stuck, little red dots, not because it was scientifically precise. The technical term was broadline H-alpha emitters, but because it was honest. They were little, they were red, they were dots, and there were hundreds of them. The question was, what were they? Here is where the mystery deepens. When you look at a distant object through a telescope, you are not just collecting light, You are reading a story written in wavelengths. Every chemical element absorbs and emits light at specific frequencies, leaving a fingerprint in the spectrum. And the way those fingerprints are stretched toward the red end of the spectrum tells you how fast the object is moving away from you, which tells you how far away it is, which tells you how old the light is. The little red dots have a very specific spectral fingerprint. They show broad hydrogen emission lines, meaning gas around them is moving at extraordinary speeds, roughly 2 million miles per hour. That kind of motion does not happen in a quiet galaxy. It happens when gas is orbiting something extremely massive and extremely dense. Something with gravity powerful enough to whip hydrogen atoms to a significant fraction of the speed of light. That is the signature of an active black hole. A supermassive black hole actively consuming matter, surrounded by a swirling disk of superheated gas called an accretion disk, radiating energy across the electromagnetic spectrum as matter spirals inward and is compressed into oblivion. But that is only the beginning. The problem is the mass. Standard cosmological models predict that black holes grow gradually, starting from small seeds merging over time, accumulating matter at a rate capped by a physical limit called the Eddington limit, which is essentially the point at which the radiation pressure from a feeding black hole pushes outward hard enough to halt further accretion. You cannot, the physics says, grow a black hole arbitrarily fast. And yet the masses being inferred from the little red dots suggest black holes that are, in some cases, wildly more massive than they have any right to be given their host galaxies. In mature local galaxies, there is a well-established relationship between the mass of a galaxy and the mass of the black hole at its center. A galaxy with 1 trillion stars has a black hole of a certain size. The ratio is consistent across billions of galaxies observed across cosmic time. In the little red dots, that ratio is shattered. The black holes appear to be overmassive, far too heavy relative to their surrounding stellar populations. Some estimates put them 1 to 2 orders of magnitude above what the local scaling relations would predict. 1 to 2 orders of magnitude, that is 10 to 100 times too heavy. Either the models are deeply wrong, or something happened in the early universe that no existing framework fully accounts for. The deeper problem is what they do not emit. When a supermassive black hole is actively feeding, when it is an active galactic nucleus, or AGN, it radiates across a broad range of the electromagnetic spectrum, radio waves, ultraviolet light, and especially X-rays. The accretion disk around a feeding black hole gets so hot, so compressed, so energetic that it produces enormous quantities of X-ray radiation. Every known AGN we have ever observed, from nearby quasars to distant feeding black holes, is a bright X-ray source. It is one of the defining signatures. The little red dots barely emit X-rays at all. Researchers who looked for X-ray counterparts in archival data from NASA's Chandra X-ray Observatory found them to be remarkably faint, orders of magnitude fainter than expected for black holes of their inferred mass and luminosity. Some showed almost nothing. It is as if the most powerful engines in the early universe are running in near silence across one of the most diagnostic wavelengths we know how to use. This is where it gets genuinely strange. You have objects that look like feeding black holes. They have the gas velocities of feeding black holes. They are red in a way that resembles dust-reddened black holes. But they do not produce the X-rays that feeding black holes should produce. And they are embedded in host galaxies that are too small, too dim, too underdeveloped to have grown a black hole that large by conventional means. Taken together, this is not a minor anomaly. It is a cascade of contradictions, each one deepening the next. And this is where the real question emerges. Not what are these objects, but what does their existence mean for the first chapter of the universe? Close your eyes for a moment and try to picture it. You are not inside a galaxy. You are not near a star. You are in the deep universe, approximately 600 million years after the Big Bang, in a region of space that has no name, no address, nothing nearby that would comfort or orient you. The cosmic microwave background still faintly warms the universe from all directions. The afterglow of creation itself still radiating at a temperature that would register as a few degrees above absolute zero. The large-scale structure of the cosmos is just beginning to coalesce. Vast filaments of dark matter and gas pulling matter into the first knots and nodes of what will eventually become clusters of galaxies. And in one of those nodes, something is happening. A region of space, compact, perhaps no larger in radius than a few light days, is blazing with energy. If you could see it from a distance, it would appear intensely red, its light red shifted even further by the expansion of the universe between that moment and the detectors that will one day receive it. But up close, it is something else entirely. It is dense, incomprehensibly, suffocatingly dense. A black hole sits at the center, perhaps already carrying the mass of millions or even hundreds of millions of suns. Around it, a cocoon of ionized gas, not a clean accretion disk, but a thick, churning shroud that absorbs the high-energy radiation pouring outward from the feeding event and reprocesses it, softening it, converting X-rays and ultraviolet photons into the optical and infrared light that eventually reaches us. That is why there are no X-rays, not because the black hole is inactive, but because the cocoon swallows them. The gas is so dense, so opaque that the X-rays never escape. They are absorbed, thermalized, and re-emitted at lower energies. The black hole is not quiet, it is muffled. Gas spirals inward at millions of miles per hour, radiating as it falls. The black hole is growing, fast, possibly faster than the Eddington limit should allow. And yet here it sits, already massive, already dominant, before most of the stars in what will eventually become its host galaxy have even formed. A black hole that outgrew its own galaxy. Now the story gets stranger. In early 2025, researchers working with high-quality JWST spectra published a finding in Nature that restructured the entire picture. They found that the broad emission lines in little red dots, the lines that had originally suggested enormous black hole masses, potentially hundreds of millions of solar masses, were not actually caused by gas orbiting that fast at all. The lines were being broadened not by velocity but by electron scattering. Electron scattering is a process by which photons passing through a dense plasma of free electrons get deflected slightly, changing their apparent energy, if the plasma is dense and compact enough. Within the range of light days, the spectral lines blur and broaden in a way that can be mistaken for Doppler broadening from high-velocity gas. The implication is striking. The intrinsic black hole masses, when calculated from the narrow cores of those same lines rather than the broadened wings, come out 2 orders of magnitude lower than previous estimates. Not hundreds of millions of solar masses, potentially hundreds of thousands, or a few million. On one hand, that relieves some pressure on the timeline problem. Smaller black holes are easier to explain in the early universe. But on the other hand, it deepens the mystery of what exactly is emitting this much light from such a small, dense ionized volume. And it means the full census of what we are seeing is still genuinely unsettled. As of 2025, over 300 confirmed little red dots have been cataloged. Researchers estimate the real number is probably much higher. Some surveys suggest they were among the most abundant type of compact object in the early universe during that brief window between 600 million and 1.5 billion years after the Big Bang. And then, mysteriously, they appear to vanish. After about 1.5 billion years post-Big Bang, the little red dots essentially disappear from the record. Where did they go? Why then? The answer depends on something we still cannot fully measure. Several competing theories are now in active contest. The first and still leading interpretation holds that the little red dots are active galactic nuclei, black holes that are actively accreting. The redness comes not from dust as originally thought, but from the dense cocoon of ionized hydrogen gas that surrounds them. This is the picture consistent with the 2025 Nature study. Young supermassive black holes enshrouded in a thick gaseous shell growing rapidly in the first billion years of the universe. The second theory invokes a more exotic origin: direct collapse black holes. This is a proposed pathway, theorized before JWST launched it, in which in the early universe massive clouds of pristine gas collapsed directly into a black hole without passing through a stellar phase at all. No star, no supernova, no gradual accumulation, just gas, gravity, and an almost immediate descent into a singularity. These seeds would be born heavy, potentially hundreds of thousands of solar masses at birth, which would give them a head start on the growth problem. A 2026 study led by researchers at the Center for Astrophysics at Harvard and Smithsonian ran radiation hydrodynamic simulations of direct collapse black holes accreting within dense early universe environments. Their simulations, they reported, reproduced the specific characteristics of little red dots: the weak X-ray emission, the absence of star formation signatures, the compact sizes, the abundance and redshift distribution. A third theory, proposed by Fabio Pacucci and Avi Loeb at Harvard, suggests the little red dots formed in extremely rare dark matter halos that were spinning very slowly. The slow spin allowing gas to collapse inward without being flung outward by centrifugal force, creating an unusually dense and concentrated star-forming environment. None of these theories is universally accepted. The field is moving fast, and each new JWST observation adds both clarity and complication. The frightening part is not what we know. It is what we still cannot rule out. Let us be precise about the stakes. Astrophysics operates on a framework called lambda CDM, or the Standard Model of Cosmology. It is one of the most tested and successful scientific frameworks in history. It correctly predicts the large-scale structure of the universe, the abundance of light elements, the patterns in the cosmic microwave background, and the accelerating expansion of space itself. It is not a rough sketch. It is a precision instrument refined over decades of observation. The little red dots, if they are what the AGN interpretation suggests, strain that model in at least two distinct ways. First, the abundance. There are simply more of them than the standard model predicts should exist at those redshifts. Simulations based on lambda CDM do not naturally produce this many compact, actively feeding black holes that early. The number density is wrong. Second, the mass ratios. In a universe that builds structures gradually, the ratio between a black hole and its host galaxy should be relatively stable across cosmic time. The overmassive black holes in the little red dots suggest that at least during that early window, the black holes ran ahead of their galaxies, which means the feedback mechanisms we believe govern galaxy formation were not operating the way we thought, or were not operating yet. One popular analogy: it is as if you discovered that in the early history of a city, many buildings had enormous foundations but almost no floors above them. That is not how construction works. And yet the foundations are real, measurable, undeniable. The existence of the little red dots does not mean that lambda CDM is simply wrong. It is more likely that it is incomplete, that there are mechanisms operating in the first billion years of the universe that current models either underweight or do not yet include. Direct collapse pathways, super Eddington accretion episodes, unusually dense gas environments. But it also means that the first chapter of cosmic history is more violent, more chaotic, and more structurally surprising than we believed. And that brings us back to where we started. A grain of sand, held at arm's length against the dark. The James Webb Space Telescope pointed at patches of sky that small and found the universe doing something we did not expect, not in one place, not as an anomaly, but everywhere it looked, scattered across every deep field like sparks from a fire that burned 13 billion years ago and whose light is only now reaching us. The little red dots are tiny. That is the word that keeps coming back. They are compact, faint by the standards of quasars, and almost invisible to every telescope that preceded Webb. They existed for a brief window in cosmic time and then disappeared, either growing into the quiet behemoths that now sit at the centers of mature galaxies like our own Milky Way, or dissipating in ways we have not yet traced. What they are telling us is still being decoded. The science is alive, contested, evolving week by week as new spectra come in and new models are tested and old assumptions are revised or discarded. But here is what they have already established beyond any doubt. The universe began building its largest structures earlier and through stranger mechanisms than we knew. The black holes at the hearts of the earliest galaxies did not wait their turn. They arrived first. They grew fast, they burned bright, and for a window of about 1 billion years, they were everywhere. The universe apparently was in a hurry, and we had no idea. If the early cosmos looks this different from what we expected, the question worth sitting with is not just what the little red dots are, but what else is out there waiting in the deep infrared, patient and invisible, for the right eye to finally see it. The next image might already be on the way. If this changed how you see the early universe, the next video goes even deeper into what JWST is still finding that no one has a good explanation for yet.